Okay, so now how do we prove that? So, so the first thing we observe is that if we take, if we're looking at, suppose that Fn and F here, suppose that this, suppose that Fn of x minus f of x, suppose that this thing here was less than epsilon over 3 b minus a. Okay, suppose you have that. And you can, of course, this here can be achieved, right? This here can, so epsilon is now given, right? And so you have that, so maybe I should just say that, so epsilon is given, so since Fn converts to F uniformly, this means that there exist capital N, so that if you're further out than capital N, then actually you have this thing here, right? B minus B and A are fixed. This is just something fixed. So this is just another epsilon, right? Sure. Okay, so if you have that, now suppose you take, so remember we defined when we when we had the partition had the dividing point with dividing points. Xi, so we were looking at these small intervals xi from xi minus 1 to xi, and we're looking at the sup of the function. So if you're looking at the sup of, suppose you're looking at, so this here is on this little interval, but it's for f, right? But the function f here, you see the function, so you have that f of x, this function here, sorry, I don't even need the absolute value, but f of x is less or equal to f n of x plus, of course, f of x minus f n of x. Right. And so this means that this thing here is, right, this thing here is less or equal to fn of x. This thing here is bounded by the absolute value of it. Right, and so this thing here, so this is fn of x, and this here is just epsilon over 3 b minus a, like that, right? So this means that if I take the sup on this little interval of f, then it's bounded by the sup of this function plus that number. Right. So I have that. So I have that. So I have that again the sup of f on this little interval. This is what we call mi of f, that this is less or equal to, because of this inequality, is less than the sup of fn of x on the same little interval plus epsilon over 3 b minus a, right? And likewise, for the inf. So again, I let little mi of f, this is now the infimum on this little interval, on this little interval of f, right? Sorry, here I wanted to insert what this thing was. So this is m, right? This, the notation for this soup here is m I fn. Right. And the infimum for f on this little interval, the notation for that is this little m, right? I refer to the interval, f to the function. And so similarly, if you take the infimum, then the infimum, and you compare it to the infimum of these fn on the same interval, then the same argument with obvious changes means that mi f here is now bigger or equal to mi fn minus epsilon over 3 b minus a. Okay? It's the same thing. Okay, maybe I'll just explain it, but it's the same sort of thing that you take. Oh, maybe I shouldn't erase this one. So it's a sort of the same thing that you're looking at. You have f of x, again, is equal to fn of x plus fn plus f of x minus. Right, so you have obviously this. And so this means that f of x is bigger or equal to fn of x minus, if you think that this here becomes negative, and the maximum it can become negative on this little interval here, on this little interval. The worst this here can become negative is epsilon over, actually for any interval, is this, like that, right? So you always have this. Okay? And so if you take now the infimum on the little interval, then you're getting mi f bigger or equal to mi fn minus epsilon over 3 b minus a. Right, so you have that. So, and that's what we claim over there. Okay, so we have this thing here, and we have the corresponding thing. This is less or equal to the maximum of the function on the same interval, and then then this equality here. This equality here was that it's bounded by this guy here plus epsilon over 3 b minus a. Okay? So this is for the little m's, the little mi's, and the capital Mi. And now we need to sum these guys, and we need to multiply those with a delta xi. So this means that if you're looking at, so what we're interested in is we're looking at this times delta xi. This gives you this gives you the lower sum of f with respect to this partition, right? Where you're summing here over the I. If you're summing the soups, then you're getting the upper sum, like that, right? And so now, you take this equality, this inequality, the string of inequality, and you're just multiplying by delta xi on both sides, and then I'm summing, right? So if I multiply, so let's call this here star. So multiply star by delta xi and sum over I, right? If you do that, then what you get is you're getting mi fn minus epsilon over 3 b minus a times this, times delta xi. This is less or equal to mi f delta xi, which is less or equal to this one here. Sorry, and I should also summing over I, like this. And then I have one more inequality, namely this right-hand side, so less or equal to, I'm summing over I, and I have, this is mi f plus epsilon over 3 b minus a times delta xi, okay? So we have that. Now let's try to figure out what this means. So this here, so now if you multiply this out, the first thing, right, the top left corner, that gives you, when you multiply the bracket out, the first term you get is the MIFN times delta xi. But that is just the lower sum with respect to the partition P for Fn, right? But then you get another term, which is you get one other term, you get this minus, and then you're summing over the I of epsilon 3 b minus a times xi, right? And then then it's less or equal to the thing, the term up there. That's just the lower sum of f with respect to the partition. The next term is the upper sum of f with respect to the partition. And then the last inequality, the first term, when you multiply this bracket out, the first term here is, and unfortunately there was a missing n. I copied it from here, sorry. There was a missing n, I just copied it from this one. Right, so now when you multiply this bracket out, the first term you get here is so you're getting less or equal to the first term you get there when you're summing over the I. That's exactly U Fn P. And then the second term you get is this I epsilon over 3 b minus a delta xi. Now, this thing here, when I'm summing here, right, then this is just a constant. So I can just pull that constant out. And the sum of these differences, that just give you b minus a, right? So if you put that in, and this exactly the same you get on this term, then you have that L f Fn p minus epsilon over 3 is less or equal to LF p, and which is less or equal to UFP. And this is less or equal to UFN p plus epsilon over 3. Okay, now what have we used so far? So far, we have just used P was any partition, and all we have used is that the Fn converts to F uniformly, and then for this given epsilon, we chose this capital N sufficiently large, right? But now, now you see that now we can just fix. So now we just let little n. We just said let this be equal to this capital N, right? We just need to use it for one little n. And so, and then we can, and now we have that since this particular function, this one function, was integrable, then there exists a partition. But this is now a partition that comes from, right, it's determined from this function here. But there exists a partition so that the difference between the upper sum for this function minus the lower sum for this function is less than, say, epsilon over 3. Okay? But so you see that this number here, right, so you see that the difference, now I can erase this thing here. So now, the first, so we observe now that this number here, because of this this number is always larger than that, right? And so this means that this thing here is, right, this inequality just tells you that this is less than, that this thing here, let me continue here below, that this thing here is less than LFN P plus epsilon over 3. This is coming from that this one here, just moving this over on the other side, then you have that this is bounded by that, and then you have another epsilon over 3. Right? And so you see that those two things, this here and that here, is squeezed in an interval of length epsilon, right? So this means that the difference between these two is bounded by epsilon, right? So, so LF with respect to this partition and UFP, right? They are both lie in an interval of length epsilon, right? So it means that the difference between the two, right? So the difference between, so this here, which is always positive, but this here, the difference must be less, I guess less or equal to, it doesn't matter. Right. Okay, so, and this proves, so this show, right, so this show that f here is integrable. It's integrable. right? Because to show that this function was integral, we just needed to, for a given epsilon, we needed to find a partition so that the difference between the upper and the lower sum was less or equal to epsilon, right? So the function f is integrable. Now I claim that it also proves that it also shows that the limit is what it should be. Right, because you see that we now know that the function, so we have now that this integral of f dx, this exists, right? Because we proved that it's integrable, so it means that this exists. And this is always squeezed between, for any partition, it's always squeezed between these two things, right? But now you see that, so this means that it would have to lie in this string of inequality. It would have to lie here between these two numbers, right? But this thing here, you know, if you make these, right, so we have also, right, so what do we have? We have that so we have that this integral here from a to b of f dx is less or equal to u f with respect to any partition. The same thing here. And now if we use this, if we use that for this given epsilon, that n here was bigger than capital N, bigger or equal to, then we have that this thing here was bounded below, from this inequality, L Fn p minus epsilon over 3. And we had that it was bounded from above. So this is just this inequality, u Fn p plus epsilon over 3. And so now we made use of, and so we do this for this capital N. So in particular, it holds for capital N. And now we made use of that. So now all I want to do is here, I want to estimate the difference between this integral here and this integral here and the integral from a to b of f capital N. Right? And I want to prove that if I'm very far out, this here is very small. Right? But I now make this one here. So if I take, when I choose my partition, so that this number here, so then I can just make sure that this number here, when I prove the, when I choose the partition, then I just said that I choose the partition so that this thing here minus this lower here for this capital N, that this here was smaller than epsilon over 3, right? And so this means again, but now you see that this integral of this integral here, this is always squeezed between these two numbers. So this is always squeezed like this. Right? And so now you see that this means that that this integral is in this interval here. But in fact, of course, in this interval between these two numbers, between actually these two numbers, by even if there wasn't a plus, in that interval, that this integral here would also lie, right? So it lies even more comfortable in this larger interval where you're adding epsilon over 3 and subtracting epsilon over 3. So this integral lie between these two. The same is the case for this. And this interval, again, have length epsilon. So this means that this difference between these two numbers is also less than epsilon. Right. And so this really proved that if it was sufficiently far out, then the difference between these two integrals was bounded by epsilon. Right? So this proved that the integral are converging. Okay. Let's look at, so how do we use this? So what we were interested in was using this fact in the case of a power series. So let me just look at an example for that. So suppose that En of x, so this is the same as in the previous example, where I'm summing here from k equal to 0 to n xn over xk, over k factorial. Right, so these are the function xn, and x is just, en, and the function, so this is the function en. The function e is just the exponential function, so which I think about as the infinite series, the power series, like this. And now so we already observed that by the Weierstrass, by Weierstrass, M-test, by Weierstrass M-test, the En converts to E on any interval. You have to restrict the interval, but if you're fixing an interval like this, then it's converging uniformly, right? So this is what Weierstrass M-test gave, right? And now these functions here, they are polynomials. The En are polynomials, so it's easy to integrate them. So you have that the integral here of En dx from, let's say, some interval from a to b, this thing here is now equal to the sum here. So now it's just a finite sum, so you can exchange that. And then you're integrating from a to b of xk over k factorial. And of course, that's very easy to do, right? So dx. And the theorem that we just proved is that this thing here is, because the convergence is uniform, each of these is integrable. This means that the limit here is also integrable, and the integral of the exponential function is the limit of these integrals, right? And so the point here is, again, is that if you have uniform convergence, then you can sort of, you're using the uniform convergence that we have from Weierstrass M-test, then we can interchange this infinite sum with taking integrals, okay? Let me just, I had wanted to do one more thing, but I don't have time to do that quite. So I'll pick up on that next time, but let me just observe that when you're integrating here, when you're integrating this thing here, right? So what is the integral of this? So when we're just calculating this, so you're integrating x to the k over k factorial. When you're integrating a polynomial, you're using the fundamental theorem of calculus. So you're trying to look for a function whose derivative is this, right? Such a function is often called the antiderivative. And so what is that function? So a function, so if you're looking at x to the power k plus 1, right? So you know that you have to, because of polynomial, you have to add 1, right, to the exponent. And then this, as when you take derivative, this comes down. So you have to look at k plus 1 factorial, right? Because if you take, when you take the derivative, then k plus 1 comes down and it kills the first one, and the rest is this, right? And so, so when you evaluate this integral, then it's this here is the antiderivative, and you have to insert the boundary values like this, right? So that it would be the integral. Right? Okay, so I'll just stop here, and next time I'll go through the one theorem I didn't get to, which is how to interchange the differentiation and right, if you take a sequence of functions that converge uniformly and you want to take the derivative of these, how do you relate the derivative of the sequence to the derivative of the limit? Okay, so, but it's in the notes. I already posted the notes, but I'll go through that next time. Any questions? Yeah. Yeah.
I think originally, it started saying that we wanted the difference to be less than epsilon, and that was less than or equal to epsilon.
Yeah,
okay.
That's okay, right? Because, right, so I'm not 100% sure I needed epsilon, less or equal to epsilon. It doesn't really matter, right? Because you just picked that. I had chosen it with the epsilon over 3 and epsilon over 3 times b minus a. That was just to have it worked out, so it was epsilon in the end. But you could, of course, have chosen it even smaller than you would have had strict inequality. It's possible it was actually strict inequality. Anyway, okay.